Hi everyone, this is Haehyun Cho. I'm a PhD student of Arizona State University. In this talk, I'm going to present SmokeBomb that can effectively mitigate cache-side channel attacks on the ARM architecture. This work has been done jointly with Samsung Research. A CPU cache is designed to reduce the average cost to load data from the main memory. A processor can access to a cache really fast, but the size of a cache is very small. Therefore, we only can temporarily store limited amount of data in a cache. Basically, cache-side channel attacks are to identify which data is in a cache by exploiting time differences between an access time to the main memory and an access time to a cache. To infer the sensitive data, attackers can check an access time to some data. If an access time is very fast, it indicates that the data is in a cache, which also means that the data was used by a victim process. There are various types of cache-side channel attacks. We can first categorize them by the location of the targeted cache. There are single-core add-on data cache attack, cross-core add-to-cache attack, and cross-core add-on cache attack. Also, cache attacks can be further categorized by attack timings and attack methods. In this work, we aim to prevent all possible cache-side channel attacks for inclusive and non-inclusive caches of ARM processors. The reason behind we couldn't consider the exclusive cache is among all the ARM processors, only the Cortex-A55 uses the exclusive cache, but there were no available devices on the market. Therefore, we couldn't conduct any experiment using the exclusive cache. As a result, the exclusive cache became out of scope in this work. In inclusive caches, cache lines of the add-to-cache will not be evicted by new data as long as the data is stored in the add-on cache. In non-inclusive caches, a cache line in the add-to-cache can be evicted to make space for new data, even if the line is present in the add-on cache. Our protection mechanism, SmokeBomb, was verified on these cache models. I'm going to use the following three terms in this presentation. First, sensitive data is secret or could be used to infer secrets. For example, the t-table of AES algorithm is sensitive data. Key data is the subset of the sensitive data that is actually put into the cache during the execution. Therefore, the attacker's goal is to use a cache-side channel attack to infer which sensitive data is the key data. Lastly, we refer to code that uses the sensitive data as the sensitive code. I'm going to discuss about the root cause of the cache-side channel attacks and the core idea of SmokeBomb to show how we can mitigate the cache-side channel attacks. While executing the sensitive code, the key data is temporarily loaded into a cache, and after the sensitive code terminates, the key data is gradually evicted by other data. Between 2 points, the time when the sensitive data is loaded onto a cache and the time when the sensitive data is totally evicted from a cache, data changes in a cache can cause important information leaks. Attackers exploit such temporal data changes in a cache using various attack methods. Their goal is to find data used by the sensitive code. To this end, Cache attacks typically consist of the three steps. First, attackers make a cache to be a known state by flushing or loading some data. And they wait sensitive data finishes. Lastly, they check data changes of a cache. To mitigate the cache side channel attacks, we designed SmokeBomb. The core idea of SmokeBomb is to use the add-on cache for the sensitive data so that it can give consistent attack results. Because the add-on cache is a per CPU cache, which is not shared with other cores, a process can exclusively use the add-on cache. However, there is no mechanism to select data that cannot be loaded into the cache or that must be loaded into the cache. SmokeBomb exclusively uses the add-on cache for the sensitive data while sensitive code is executing. It first preloads always the same amount of sensitive data to the add-on cache when the sensitive code starts to execute. Next, it preserves loaded data until sensitive code finishes. Therefore, attackers will think there is no data changes regarding the sensitive data while the sensitive code is executing. Lastly, it flushes out the sensitive data from the cache. So by SmokeBomb, attackers will always get consistent attack results because there will be always the same amount of sensitive data in the add-on cache, or there will be no sensitive data in the cache. For example, if an attacker checks access times to the sensitive data in the middle of sensitive operation, attack results will be all cache hits. If an attacker checks access times after the sensitive code terminates, attack result will be all cache misses because there is no sensitive data in the cache. SmokeBomb consists of two modules, an LLVM instrumentation pass as a compiler extension, and a loadable kernel module. The compiler pass automatically modifies source code of a program at LLVM IR level. It inserts API calls and patches cache-relevant instructions to instructions that we defined and software emulated during runtime. SmokeBomb protected programs run with the kernel module that provides actual functions for mitigating cache-side channel attacks. Let's take a look from the instrumentation process in detail. Instrumentation pass requires an annotation on the sensitive data. Based on this annotation, it modifies a program automatically. It first finds functions where sensitive data is used. Then it inserts SmokeBomb APIs before and after the sensitive code. SmokeBomb is initiated by the init API, which preloads the sensitive data to the add-on cache. And SmokeBomb is finalized the exit API that flushes out the sensitive data from a cache. Next, we need to preserve the sensitive data while executing the sensitive code. However, most ARM processors do not have cache locking instructions. We utilize the undefined instruction exception handler to implement our own cache locking instructions that are software emulated by the handler. SmokeBomb finds and patches cache relevant instructions like load and store in the sensitive code. But we only patch instructions that access to non-sensitive data. This is because after preloading the sensitive data, they can change the cache state by fetching non-sensitive data to the add-on cache. At runtime, those instructions will be trapped and handled by SmokeBomb's exception handler. The patched instructions perform the intended operation of the original instruction, but also ensures the preservation of the sensitive data in the Aaron cache. In the preloading phase, SmokeBomb preloads the sensitive data to the Aaron cache. Processors typically implement the pseudo-randomly placement policy for caches. Therefore, we need to bypass the randomly placement policy. Otherwise, sensitive data loaded by SmokeBomb can be evicted by another sensitive data while preloading it. Through some experiments, we found that if a cache line is flushed, new data is fetched to the flushed cache line. So we repeat flushing and fetching a cache line until preloading is done, as shown in the below figure. Please refer to our paper for more details. For optimizing this process, we used the preloading data instruction. The PLD instruction can load data into the cache much faster than the load instruction. Preserving sensitive data accomplished by SmokeBomb instructions. We handle software-defined instructions through our undefined instruction handler. In the instrumentation phase, we patched cache-changing instructions that access non-sensitive data. Therefore, only our SmokeBomb instructions can evict the sensitive data from the Aaron cache while the sensitive code is executing. If sensitive data is evicted by SmokeBomb instructions, we refit it as shown in the figure. We note that we can't know which cache line was evicted because of the pseudo-randomly placement policy. Therefore, we need to flush an entire set and refill the set. Lastly, we need to flush out the sensitive data from the cache. Even though it seems safe to leave sensitive data in the cache after the sensitive code terminates, we found that not flushing the sensitive data can cause information leaks, especially in the RIU caches. We implemented and evaluated SmokeBomb on two different ARM processors with different instruction sets and cache models. Also, they use different replacement policies. So we believe that our experimental environments can represent the most ARM processors. First, we evaluated the effectiveness of SmokeBomb with the AES algorithm in the OpenSSL library. As these attack results show, without SmokeBomb, attackers can clearly distinguish the key data. However, with SmokeBomb, attackers can only have either all cache hits or cache misses. We also evaluated the effectiveness of SmokeBomb with the decision tree. Without SmokeBomb, attackers can find input attributes and the output decision. But without SmokeBomb, attackers can only have either all cache hits or cache misses. Next, we measure the performance of SmokeBomb instructions and APIs. As the left table shows, execution times of SmokeBomb instructions are substantial. Therefore, the more SmokeBomb instructions that execute, the larger the resulting performance overhead. To avoid unnecessary performance degradation, SmokeBomb handles the performance overhead of executing SmokeBomb instructions by patching only the cache-changing instructions in the sensitive code that access non-sensitive data. The right figures show the execution times of each API that increases with the size of the sensitive data. To understand the impact of SmokeBomb on the performance of sensitive code, we first evaluated a SmokeBomb protected AES program in the 7-zip application. The left figures show the performance overhead. The AES algorithm is a block cipher, so the performance overhead brought by SmokeBomb APIs and instructions has to be overlapped as an info file has more blocks. Also, we applied SmokeBomb to HTTP secure protocol implementation. Then we compared average execution times required to download the 500 web pages between the normal HTTPS protocol and SmokeBomb protected one across 5,000 experiments. The right table shows SmokeBomb protected HTTPS protocol has very low performance overhead. Lastly, to evaluate the impact of SmokeBomb on systems throughput, we compared throughput when SmokeBomb is not running with when SmokeBomb is running continuously. Therefore, the result can show how the system performance changes when SmokeBomb is activated. The result illustrates that when SmokeBomb is activated, the average performance overhead that SmokeBomb imposes on the overall system is negligible. SmokeBomb has several limitations. First, SmokeBomb can't mitigate instruction cache attacks and cannot provide protections for exclusive cache models. Also, while the concept of a private space in the add-on cache is not ARM specific, SmokeBomb is implemented for and heavily used specific functionality of the ARM architecture. In this talk, I presented SmokeBomb, a systematic software approach to defeat cache-side channel attacks on the ARM architecture. Our approach protects access patterns on the sensitive data from attackers. Thank you for listening.